Hey folks, I'm going to run through a few of the homework problems from the Stoichiometry / the mole assignment. I've had a few students ask questions about things, mostly about the syntax, but since this is the first time that we're using chemistry units, namely Avogadro's number, moles, stuff like that, I think that it's important that we work through some of the basics together too. So let's dive right into it. The first couple of questions are not like the others. They're just going over how we find our atomic masses given a series of different isotopes. So let me hop into presenter mode here. Okay. Element R has 3 isotopes. They are present in 0.0398, etc., relative abundance. Now, this term relative abundance sounds fancy, but really all it's saying is percent without the times 100. Whenever you have a decimal value less than 1, you can treat it just like a percentage, just you don't need to do that divide or multiply by 100, depending on which direction you're moving in. If you add these 3 values together, you find that it does add up to 1 instead of 100%. We're given their respective masses, and so what I want to do now is calculate the atomic mass of this element. I'm going to start by selecting my pen. There we go. I'm going to start by taking each of the different isotope masses, so 193, 174, and I have 153, and I'm multiplying each of these values by their corresponding relative abundance. So the first one will be times 0.0398, the second one 0.1614, and the final 0.7988. I'm going to grab a calculator real quick and plug these values in. What we should find at the end of all of this is a value that is somewhere in between 153 and 193. I'm assuming it's going to be closer to 153 because most of our element is that particular isotope. So for the first one, I got 7.6. Oh boy, sorry. It's a new tablet. I am still mapping some of the buttons, so forgive the occasional mess up here. 6814. We don't want to truncate those decimal places until the very end. If you cut them off early, you might end up getting an inaccurate value. That's true for all scientific measurement and calculation. You don't do any rounding or truncating until the very end. Otherwise, you do a thing which is called propagating error, and we don't want that. And for the last value, I get 122.2164. Now what do we want to do with all of this information? Well, I'm just going to add all of these together, and that should give me the atomic mass of my element. 7.6814 plus 28.0836 plus 122.2164. And sure enough, I find a value that is in between all of those, and as I expected, much closer to our last value there, because most of it, roughly 80%, is that lighter isotope. Now it's saying don't give a decimal point here, so what I'm going to do is I'm going to round up this decimal to the next value, which is going to be 158. And so that should be our answer, but not to that question. Whoa, that's new. But we got it right anyway, despite what's happening there. Yeah. Keep in mind, folks, if you haven't noticed, this little gray box that pops up when you click inside our answer box has some really helpful information. For example, it's expecting 3 significant figures here. And so that's a good way to check your work and make sure that you're answering the question correctly. Moving right along to the next one. C6H14, that is our chemical formula, and we want to calculate its molar mass. Molar mass, again, sounds fancy, but what you're going to do is you're going to head over to a periodic table, find the different elements, and then figure out how many of those different elements there are in your compound, add all of those values together. So I like to break this up into steps, especially when we're still learning. So we'll start with carbon. Carbon has an atomic mass of 12.01. Hydrogen has an atomic mass of 1.008. These are values I'm reading directly off of a periodic table. This is in terms of grams per 1 mole. On your periodic table, it might say AMU instead, but AMU and grams per mole actually mean the same thing. Now what I'm going to do is I'm going to multiply these values times the number of each element we have. The subscript tells us how many of each thing there is, and so I have 6 carbons and I have 14 hydrogens. Because we're just counting the value of these things, there is no unit to worry about, and we don't worry about significant figures either. Once I've done all of that, I should get some values here. All right. Still figuring out the pen, sorry. So we get values here. 6 times 12.01 gives us 72.06. .06, and 1 times 14 gives us, well, roughly 14. I don't think that this decimal is going to matter in the end, but I'm going to put it in anyway, 0.112. And of course, these are both in terms of grams per mole. And then to find our final molar mass, I'm just going to add these two values together, 72.06 plus 14.112, and I get 86.172 grams per 1 mole. Now, there is no place to put units in on your homework assignment, so don't start trying to type that stuff in. It's just looking for the numbers here, all right? Yes, on exams and when doing scientific writing, we would expect you to include that information, but here they've already given you the unit. And so we're going to type this in, 86.172. And there you have it. Now, it really shouldn't have given us this because it said to 2 decimal places, but that's okay. Next on our list, how many molecules of this compound do we have? Now, when you're looking for number of molecules, it's a little bit of a different calculation. In order to begin, I'll write what we're given. It's always a good idea to write down what you're given, 7.70 moles of C9H18. This is our unit, and this is our chemical identity. I think that it's important to have both of these pieces of information down when we start to solve these problems. You're going to see later on in the semester that we're switching in between 2 different chemical identities as we start doing some actual chemistry calculation, and so it's really helpful to have all of this information down from the beginning so that we just get into the habit. Now, if we're going from molecules to moles, or vice versa, the value we need is called Avogadro's number. It's something like 6.022 times 10 to the 23rd. Particles per 1 mole. The reason I generalize it to particles per mole is because you can technically have a mole of anything. Now, atoms and molecules are generally speaking, pretty small things, and so it makes sense to count them in terms of moles. However, you might also have like a mole of sand grains or a mole of stars, stuff like that. These would be huge quantities of those things, but I digress. It's just like using the word dozen. It's just a way of counting a grouping of things in a convenient way. So our particle in this case gets a little bit more specific here. We have molecules, but the good news is that you can just swap molecules in for Avogadro's value here. So I'm going to be multiplying this by 6.022 times 10 to the 23rd molecules per 1 mole. This is how I like to set up dimensional analysis problems, because you can very easily see that we are canceling out moles from the numerator and then the subsequent denominator, and then this whole thing gives us our value. That's 7.70 times 6.022 times 10 to the 23rd. And I got a value on my graphing calculator that is 4.63694, and it says E24. Now, many of you have been taught by your high school algebra teachers that E isn't acceptable and you need to change it into times 10 to the something. You would write this as times 10 to the 24. However, we don't have superscripts and subscripts when we're using the Luminome homework system. And so to keep things simple, I just expect you to write exactly this, E24. It also says to do that at the beginning of the homework assignment, and this is how we're going to enter scientific notation for all of our homeworks moving forwards. And so I'm going to go ahead and try that out. Where are we? Here we go. Okay. It's asking for 3 sig figs. Make sure that you round appropriately. So it should be 4.64 because the 636 would round up to 64. And then I'll put an E and then a 24. You don't have to put the plus. I think it's still counted as correct if you do put the plus. Yeah. But if it's negative, you obviously need to include the negative, which is wrong in this case because it's not negative, it's positive. But you will see some examples where it has to be included. And the last one I'm going to do for this video, consider a 4.57 gram sample of this. How many atoms of carbon are in it? This one kind of takes everything into consideration that we've been learning this chapter. We have 4.57 grams of C4H10. How many atoms of carbon would be in this sample? In order to get to atoms, I need to have Avogadro's number, which requires me to have moles. And in order to get moles, I'll need the molar mass of this compound. So I'm going to start by writing some units down over here, just things that I know I'm going to need later on. I think that Avogadro's number is a good place to start. 6.022 times 10 to the 23rd. And that's, in this case, going to be molecules, forgive the terrible handwriting, per mole. Then I need to know the molar mass of this compound. I'm going to find the molar mass by saying, well, we have 4 carbons. So C14. Oh my gosh, sorry. Don't know where I keep getting that tens place from. All right. We're going to take 4 carbons times its molecular weight. And the 10 hydrogens times its molecular weight. Then I'm going to multiply those out and add them together. 4 times 12.01 plus 10 times 1.008 is going to give me 58.12 grams per 1 mole. And that's the molar mass of this sample. So now I'm going to set up my dimensional analysis question here so that I'm canceling 1 unit every step of the way. This is a really good way to check your work as you're going through. Make sure you're setting these up correctly. In the first step, I need my grams value to cancel, so I'll put the 58.12 grams on the bottom. Grams cancels with grams. Great. Now I have moles of C4H10. I don't want moles. I want eventually atoms of carbon. So I'm going to take my molecules per mole value there, which is already in the correct orientation. Per 1 mole. And that allows moles to cancel. And this is going to give me how many molecules I have. Molecules of what? Molecules of this guy. I'm going to enter this on a new line here. 4.57 divided by 58.12 times 6.022 times 10 to the 23rd. And I get 4.74. I'm just rounding because I'm lazy and don't want to write everything out. E to the 22nd here. E to the 22nd what? Don't forget about your units. It's going to help you not make mistakes on exams. Well, it's that many molecules of C4H10. Now, some of you might think this is the final answer, but we're not asked for how many molecules of C4H10. We're asked for how many atoms of carbon are in this sample. And so in order to figure that out, I have to think, well, how many atoms of carbon are there in one of those C4H10 molecules? Turns out 4. And so what I'm going to do is multiply this whole value by 4. Or you could also think of this as another dimensional analysis question where we're converting the chemical identity, the C4H10, into its number of carbons. So there are 4 carbons for every 1 C4H10. And so I get to cancel out my C4H10s, and that'll tell me how many particles of carbon I have. We wouldn't call it molecules anymore, they're atoms now. But you get the idea. So multiplying this by 4, and I now have 1.894 e to the 23rd. And that should be our answer here. Looking for 3 sig figs, so we'll type in 1.89 E23. There you have it. Well, if you watched the video, I hope that it's helpful to you. Good luck, folks.